in case of intrinsic semiconductor. Now we are going to the extrinsic semiconductors. Already we discussed about the extrinsic semiconductors. So here there are two types of extrinsic semiconductors will be there based on the doping. So we are categorized into, so extrinsic semiconductors are two types. Okay, so first one is N type and second one is P-type semiconductors. First we will discuss about the N-type semiconductor. So when we will dope the pentavalent element such as phosphorus, arsenic, antimony is added to the intrinsic semiconductor. What happened here? Uh, See here. See, we are adding the phosphorus. Phosphorus. So phosphorus means pentavalent. These are the 5 electrons will be there. So in that 4 electrons are bonding with the surrounding silicon atoms. 4 electrons are bonding with the surrounding silicon atoms. Okay, that means phosphorus having 5 electrons will be there. So remaining 1 electron. Remaining 1 electron is does not involve in a bonding. Does not involve in a bonding. So these electron is these electron we will consider as a free electron. So that electron also donor electron. Donor electron. It donates 1 electron. Each phosphorus atom donates 1 electron to the N-type semiconductor. N-type semiconductor. So this energy, that means this energy, this is a free electron. That means nothing but so bonding between the nucleus of the phosphorus atom and this free electron is very less. Attraction between the nucleus of phosphorus and this electron is very less. That's why if you give very little amount also, what happen? It will free and it will move through entire atom. It will move through entire atom. Okay, so that's why this electron involved in a conduction. This electron involved in a conduction. Okay, this is about the N-type semiconductor. N-type semiconductor. Now see here, the intrinsic semiconductor doped with pentavalent impurities called N-type semiconductor. The energy level of 5th electron is called donor level. Here, so this level, this energy, this electron having some energy level, that energy level we will call it as donor energy level. Donor energy level. Here we are doping. So if you suppose if you will take one semiconducting material, if you dope the phosphorus, just 1 or 2%, just 1 or 2% also. So if you will take how much of free electrons will be present means, so there are nearly 10 to the power of 16 to 10 to the power of 20, 10 to the power of 16 to 10 to the power of 20 free electrons will present per unit volume. So if you dope 1% phosphorus also, so there are how many free electrons will be present means 10 to the power of 16 to 10 to the power of 20 free electrons will present per unit volume. Okay, that means that much of electrons, that much of free electrons will be present if you dope the little amount of the phosphorus also. Those all electrons occupy the one free, that means these are all free electrons. These all free electrons occupy the one energy level, that is the donor level. The donor level, yeah. The donor level is close to the bottom of the conduction band. Okay, most of the donor level electrons are excited into the conduction band at room temperature and become the majority charge carriers. Okay, hence in N-type semiconductor, electrons are the majority charge carriers and holes are the minority charge carriers. Okay, understood? Yeah. Now see here. So if the donor level, if you for unit volume, how we can say that 10 to the power of 16 to 10 to the power of 20, we can say that. So these what are the energy of this donor level means just below the conduction band, just below the conduction band. Okay, if you give very little amount of energy also, if you give very little amount of energy also, what happen? These, so energy gap between this conduction band and donor ED, so the donor level is very less, very less. So that's why if you give little energy also, what happen? These donor electrons will goes to the conduction band. Donor electron will goes to the conduction band, involved in a conduction process, Okay, now here, so in conduction band, how many electrons will be present? What is the density of electrons we have to calculate here? So what is the density of electrons in a conduction band? In case of n-type semiconductor, we are calculating. So just observe here, if you give some amount of energy, what happen? So these donor levels will goes to the this conduction band, as well as these valency electrons also. These valency electrons also will goes to the conduction band. Will goes to the conduction band. What is the total number of electrons in conduction band means? So total number of electron, that means how to calculate total number of electrons here? So some electrons from the valency band, some electrons from the this donor level. Okay, so the in conduction band, how many electrons will be present means, so some electrons coming from the donor level, some electrons coming from the valency band. So that means you compare to the donor level, so these valency band electrons are very small compared to the donor level electrons. So these valency electrons are very small because so these electrons require high energy, so to goes to the conduction band. So that's why if you will take at a lower temperature, so what are the majority charge carriers here? So that means due to the donor level, so some electrons are coming. So those all mainly, so those electrons are coming from so these donor level. So compared to the valency band, so that's why, so these excited electrons of donor level, excited electrons or ionized electrons of donor level, we will call it as, so total number of electrons in a conduction band na? Okay, so that means if you will take, so what are the free, in case of n-type semiconductor, majority charge carriers are the electrons. Okay, so those all electron, so we have to calculate those electrons here. Those are those majority charge carriers in conduction band. Okay, now, so what are the majority charge carriers means? Some electrons coming from the donor level, some electrons coming from the valency band. So compared to the donor level electrons, so these valency band electrons are very small, very small. That's why we can neglect these valency band electrons. See here. Okay. So here consider Nd is the donor concentration. Nd is nothing but number of electrons present in a donor level. The number of donor atoms per unit volume of the material. Nd also we will also call it as, so number of donor atoms per unit volume, and Ed is the donor energy level. Okay, at very low temperature, all donor levels are filled with electrons. Okay, with increase of the temperature, more and more donor atoms get ionized, and the density of the electrons in the conduction band increase. If you give the small energy also, what happen? Those donor atoms goes to the excited state. And so excited state is nothing but conduction band. Those donor atoms are goes to the conduction band. Those are involved in a conduction. Okay, now see here. So initially, so according to the intrinsic semiconductor, what is the density of the electrons in a conduction band? So here density of electrons in a conduction band, n is equal to this one. So 2 into 2 pi me kt by h square whole power 3 by 2 into exponential of ef minus ec by kt. This is according to the, what is that, intrinsic semiconductor. Okay, so that means in case of conduction band, how many electrons will be present? According to the intrinsic semiconductor. So the total number of density of electrons will be present in a conduction band equal this one. Okay, now coming to the here, in case of n-type semiconductor, so majority charge carriers are electrons. So we can neglect the holes concentration. So those all electrons are coming from the, so majority of electrons are coming from the donor level. Okay, so that's why now we have to calculate the density of ionized donor atoms. Otherwise, so density of electrons in a conduction band in case of n-type semiconductor. Okay, here Nd is the density of electrons in a donor level, but we want density of electrons in a conduction band. Okay, f of ed means so probability of finding the electron in a donor level. Probability of finding the electron in a donor level. 1 minus f of ed. 1 minus f of ed is nothing but, so here, so f of ed is nothing but probability of finding the electron in a donor level. But 1 minus f of ed means, so that means how many electrons, so what is that, escaping from the donor level. So whatever the electrons escaping from the donor level is going to the conduction band. That means 1 of f of ed is nothing but, so number of electrons will goes to the conduction band. Number of electrons will goes to the, so that means probability of finding the electrons in a conduction band. 1 minus f of ed is equal to probability of finding the electrons in a conduction band. Okay, now so this is Nd into 1 minus f of ed is the, so total density of the conduction band. Nd into 1 minus f of ed gives the total density of the conduction band. Okay, so that is equal, so that is so simply 1 minus f of ed. 1 minus f of ed is nothing but, see, I will explain you how we are writing here. So Nd is Nd, so 1 minus f of ed is equal to ed minus ef by kt. How we wrote that, so I will explain you. See here. Okay, see here. So Nd plus is nothing but X, that means ionized donor atoms. So ionized donor atoms means, so how many electrons will goes to the conduction band? How many electrons? So will goes to the conduction band, that is equal to the Nd plus. Nd plus is equal to the ionized donor atom. So that is equal to the Nd into 1 minus f of Ed. Okay, so here 1 minus f of e. F of ed according to the Fermi-Dirac distribution function, f of ed is equal to, we can write 1 by 1 plus e power minus ef minus ed by kt. Ef minus ed by kt we can write. Okay, so if you simplify it, okay, so 1 minus we are doing. If you simplify it, so send this term this side. Okay, that means what we are doing means LCM. So LCM we are doing. So if you do the LCM, so 1 plus E minus EF minus ED by KT is the LCM here. So if you simplify it, so this will goes to this side, and so if you simplify it simply, we can get the, so this value E power minus EF minus ED by KT. Okay, so here EF minus ED means energy difference between the Fermi level and donor level. So this is very small. So energy gap between the that means Fermi level and donor value is very small. Okay, that's why compared to KT. So that's why this total term is very small. This total term value is very small. Okay, that's why we can neglect this term. We can neglect this term. Simply Nd plus is equal to Nd into, so we are neglecting denominator. That's why, so Nd plus is equal to Nd into, so e power Ef minus Ed by Kt. Ef minus Ed by Kt. Okay, so this is about the C. So that's why simply instead of Nd into 1 minus f of Ed equal to Nd into exponential of, before minus we wrote, that means minus Ef minus Ed. So now here Ed minus Ef we wrote. Okay, so by Kt. So just simply if you remember this also you can do. So no need to simplify total. So just Nd into 1 minus f of Ed. So this is the density of the electrons in a conduction band. Density of electrons in a conduction band, that is approximately equal to the Nd into exponential of Ed minus Ef by Kt. Okay, so this is the density of electrons in a conduction band. Okay, so according to the intrinsic semiconductor, what is the density of electrons in a conduction band? This one. Okay, now we are equating both. Okay, so this is equal to the this one, density of electrons in a conduction band according to the intrinsic semiconductor. So this is the density of electrons in a semiconductor, intrinsic semiconductor. So this is the density of electrons in a n-type semiconductor. So for simplifying this equation, we are equating these both. We are equating this and this. Okay. Now see here, at very low temperature, the number of electrons in a conduction band must be equal to the number of ionized donors. Okay, so number of electrons in a conduction band is equal, this is the ionized donors, we said that is equal to the number of electrons in a conduction band. Okay, that's why we are equating this equation into this. We are equating both equations here. Okay, so we are equating both and we will apply the logarithm both sides. So first we are equating this and this. We are equating these two equations and we will apply the logarithm both side. We are applying the logarithm both side. Okay. If you apply the logarithm both side here, so here this is a into b. Okay, L log of a into b. We can write log a plus log b. Log a plus log b we can write. Okay, simply both sides. Both sides we are applying logarithm here. Okay. Now, so if you see here, so if you apply the logarithm here, so we can write ln of this term and ln of this term we can write. Similarly, ln of nd plus ln of exponential of ed minus f by kt. So ln of exponential means simply we can write ef minus ec by kt. Similarly, here also ln of exponential means ed minus ef by kt we can write. Okay, yeah. If you further, so the terms, so here, so this term will be, so bring, so this term I am bringing this side and so log nd minus, so this term I am bringing, so this side log of 2 into this total. Okay, if you simplify it, if you simplify it, yes. Okay, so now I am taking LCM here kt. Okay, if you simplify it here, so ef, so minus and minus plus ef here, so 2f, and if you simplify it, so minus ed, so minus of ed plus ec, minus of ed plus ec. Okay, now send the kt that side, so kt into here, so log a minus log b, log a minus log b. So here ln is nothing but log base e, log base e. Simply we can write, so ln also, so log base e also we can write. Okay, ln of a minus ln of b is equal to ln of a by b. Okay, so log of a by b. Okay, so kt into log of this by this term, this by this term. Okay, now from this equation we are calculating the Fermi level of n-type semiconductor. Fermi level of n-type semiconductor. EF is equal to ED plus EC by 2. ED plus EC by 2 plus KT by 2 into log of this total term. And this total. Okay. Now at 0 Kelvin, if you will take it 0 Kelvin, if you substitute T is equal to 0, so we can get only EF is equal to ED plus EC by 2. Okay, what is the Fermi level in case of n-type semiconductor? What is the position of Fermi level in case of n-type semiconductor? Means in between the donor and in between the, so ED and EC, in between the ED and EC. Okay, so what is the Fermi level of the Fermi level in case of n-type semiconductor? Means that Fermi level position is, so in between the conduction band and donor level, donor level. Okay, now yeah, see here, now we are calculating the density of electrons, density of electrons in a conduction band in case of n-type semiconductor. Okay, for that what you will do means, this is the Fermi level EF, this is the Fermi level EF. So this EF value, we are substituting the this in case of intrinsic semiconductor carriers, so charge carriers Ni equal to, so 2 into 2 pi, so this value. Okay, so exponential of EF minus EC by KT. Instead of EF, this EF value, instead of EF here, instead of EF, we are substituting the substitute EF value and just substitute the EF value here. Okay, then we will simplify. We can get the n value. You can get the n value. So this is the n value here. N is equal to this value. So first I am taking only this term, only that term. What is the term? Exponential of EF minus EC by KT. Okay, the exponential of EF minus EC by KT. So here instead of EF, I am substituting the Fermi level value, this value. Okay, so if you substitute that value here, okay, exponential of ED plus EC by 2 plus KT by 2 into ln of this total term minus EC by KT. Okay, so and so this KT, so this is in denominator, and separate it. If separate if individually, so this term will become ED plus EC by 2 KT plus ln of ND by, so this total term, okay, minus EC by KT, minus EC by KT. Okay, so here these two terms, so from these two terms, ED plus EC by 2 KT minus EC by KT. Okay, if you simplify these two terms, we can get ED minus EC by 2 KT, ED minus EC by 2 KT. Okay, now yeah, okay, this is ED minus EC by 2 KT, and this exponential. Okay, exponential we can send, apply the individually. So here previously that exponential term for whole, now that exponential apply the individually. So if you apply the individually, this is exponential of ED minus EC by 2 KT, and this is ln, so that means log of this total term. And if you apply the exponential means, so log exponential get cancelled. Okay, remaining term will be ND whole power 1 by 2 into 2 pi MEKT by h square whole power 3 by 2, and whole power 1 by 2 will be there. Okay, so now this term, this total term, okay, I will write this side, okay, into exponential of ED minus EC by KT. Okay, so this is the exponential of EF minus EC by KT value, this value. So substitute this value in this equation, substitute this exponential total term value in this equation. Okay, if you substitute means we can get the n value. So n, so this is the n. So in place of this total exponential term, we are substituting this value here. We are substituting this value here. Okay, see here, ND whole power 1 by 2 into exponential of ED minus EC by 2 KT. Okay, and here 1 by 2 will be there. So 1 by 2 will be there. So we can write 2 power 1 by 2 into this total whole power 3 by 2 whole power 1 by 2. Okay, so that means we can write 3 by 4. 3 by 4, 2 pi MEKT by h square, 3 by 4 we can write. 3 by 4 we can write. Okay, here if you simplify it, if you simplify this equation into, so see here, this is root 2, 2 power 1 by 2. Here 2 will be there. Okay, simply this also will become root 2, and ND also. So ND power 1 by 2. So this both are having same same power. So that's why I am writing 2ND whole power 1 by 2. Okay, and here, so 2 pi MEKT by h square whole power 3 by 2 is there. So this is 2 pi ME by KT h square whole power. This is 3 by 4. 3 by 4. This is in denominator. Okay, let us take this is A, this also A. So A power 3 by 2 by A power 3 by 4. Okay, so simply we can write A power 3 by 2 minus A power 3 by 4. A power 3 by 2 minus A power 3 by 4. Okay, simply if you solve it, so again A power 3 by 4 will come. Simply if you solve it, so 2 pi ME star KT by h square whole power 3 by 4. If we simplify these two terms, we can get, so because, so this is 3 by 4, this is 3 by 2. Okay, if you simplify it, again we can get 3 by 4, 2 pi ME KT by h square whole power 3 by 2 into, so as is exponential of ED minus EC by 2 KT. This is the density of electrons in case of n-type semiconductors. Density of electrons in case of extrinsic that means n-type semiconductors. Density of electrons in case of n-type semiconductor. Here this is nd. So it will be nd. So density of electrons is proportional to the nd. So that means nd is the number of donor levels, number of donor electron. See here. Thus we find that density of electrons in the conduction band is proportional to the square root of the donor concentration. Donor concentration at moderately low temperatures. Moderately low temperatures. Okay. See here. Now this total term. This total term already previously we discussed. That is NC. NC. NC is the so density of the conduction band. So density states of the conduction band NC. Okay. So ND is the density of the donor level. Density of the donor level. So here this total term we can simply NC. So that means N equal to 2ND into NC into exponential of ED minus EC by 2KT we can write. Okay. So this is the derivation of n-type semiconductor, carrier concentration of n-type semiconductors. Okay, simply how to do this carrier concentration of n-type semiconductor means, okay, first we will take the donor level. So that is the here nd is the donor concentration or density of donor electrons. Okay, now we are taking here not high temperatures, at moderately low temperatures. If you will take high temperatures means so that electrons. So see here. So if you will take high temperatures means so total electrons in conduction band equal to so this donor level electrons plus valency electrons also will come. Okay, at moderately low temperature means so very less number of electrons will goes to the conduction band from the valency band. So that's why at moderately low temperatures we are discussing here. So at moderately low temperatures means so only conduction electrons are only due to the these donor level only. Okay. So if you will take high temperature means so these electrons in a conduction band is due to donor level as well as valency electrons. Okay. So here total electrons in conduction band equal to so total electrons in conduction band equal to so total number of holes in valency band P plus so this Nd P plus Nd we will take, but so total number of holes at lower temperature is small. That's why we can take only so Nd is approximately equal to the so conduction electrons. See here. That's why here Nd into 1 minus f of Ed. So f of Ed is the so what is that probability of finding the electron in donor level. So but what we want probability of finding the electron in conduction band we need. So that's why what we are doing 1 minus f of Ed. So Nd into 1 minus f of Ed gives the so density of ionized donors in conduction band. Nd into 1 minus f of Ed gives the density of ionized donors. That means density of electrons in a conduction band. That equal to Nd into, if you simplify it, so Nd into exponential of Ed minus Ef by Kt. So this equation we have to equate this equation. This is so how we will get this equation means this equation is so in case of intrinsic semiconductors, what is the charge carriers? So density of charge carriers Ni equal to so this one. So this is equal to the this one. Okay. Now just we are equating both. And so we will apply the logarithm both side. We will apply the logarithm both side. If you simplify it, we can get the Fermi level. Here. Okay. So that Fermi level. So we can get Ed plus Ec by 2 plus Kt by 2 into logarithm of this some value. Okay. So here at 0 Kelvin, what is the Fermi level position? What is the position of Fermi level? So what is the position of Fermi level? I will show you here. See here. So that Fermi level position is in between the C here. So this is the Fermi level here. This is a conduction band. This is the donor level. This is the donor level. So Fermi level position. Fermi level position is in between the conduction band and donor energy level. Donor energy level. Okay. So if you will take at 0 Kelvin, what is the Fermi level means? Exactly middle of ED and EC. ED and EC. If you increase the temperature, what happens? That Fermi level is increases. That Fermi level is increases and reaches to the conduction band. See here. Okay, now we are calculating the Fermi level here. Okay, that Fermi level at 0 Kelvin, it will be middle. If with increasing the temperature, what happen? It will be increases that Fermi level and it reaches to the conduction band. This is the Fermi level value. Okay, so we'll discuss with the temperature also. So later, so this is the EF value. This EF value simply substitute in this equation. Okay, simply substitute in the intrinsic semiconductor, what is that energy density of the intrinsic semiconductor. Okay, so if you substitute the EF value in this equation, we can get the total number of electrons in a conduction band in case of n-type semiconductor will get. Okay, now further, so I am taking only this term. Okay, instead of EF, I am substituting the this value, EF value. If you simplify it, we can get the EF minus EC by KT. So just observe this one. Okay, if you get any doubt means, so just see the textbook. This calculation. So practice it. If you get doubts means, then ask me tomorrow. Okay, so just we will get the exponential of EF minus EC by KT. Okay, this total term will substitute in this equation. Okay, if you substitute means some terms will be here, so it will be cancelled. Or if you simplify it, we can get 2 nd whole power 1 by 2 into 2 pi me kt by h square whole power 3 by 4 into exponential of ed minus ec by kt. So this is the density of electrons in a conduction band of n-type semiconductor.